Welcome back to our sequence on the engineering design cycle. In this session, we'll look more thoroughly at the process of modeling in anticipation of constructing a prototype for an engineering design. There are multiple types of models that can support exploring a design more thoroughly, both to allow modification of the design and to increase the chances that the design will be successful. These models are valuable to explore an engineering design more thoroughly before investing the time, effort, and money in constructing an actual prototype. Some designs are simple or advanced enough to merit the immediate construction of a prototype. For other designs, jumping right into a prototype would be jumping the gun, especially when a design is in its early stages or is attempting to take a leap from previous designs. A model can be quite helpful to modifying, adjusting, and preparing the design for simulation or prototype construction. In this session, we'll look at the most common types of models and review how they are useful to supporting the design process. In general, models support better design. They can be physical, conceptual, logical, mathematical, or some other type of model. The mathematical model in particular supports a simulation of the design, whose results can then be used to evaluate the goodness of experimental results or can be used to test out a hypothesis regarding the function of the design. For complex systems, and also systems which require great expense, time, or effort to prototype, extensive simulation is especially important, and such simulation is nearly impossible without an underlying mathematical model. Mathematical models that feed into simulations of designs in whole or in part can have a variety of benefits. These models can reduce the costs and time involved in prototyping, supporting more accurate designs or hypotheses, and overall they can improve the quality and the efficiency of the design process. Here is a simple mathematical model that many electrical engineers and circuit designers are familiar with. The operational amplifier has a mathematical model called the ideal op-amp model, which simplifies the amplifier to the point that it can be analyzed in paper calculations by itself or in combination with more complex circuits. If the circuit designer were to use a more realistic model of the operational amplifier at the outset, it would make initial design calculations on paper or its equivalent in electronic form cumbersome or even impossible, thus limiting the ability to explore different design possibilities and ultimately to optimize the quality of the design. Once a basic design is created on paper using simple mathematical models like the ideal op-amp model shown on the previous slide, the design can be further tested in simulation programs, such as SPICE for analog circuits and Logisim for digital circuits, that use higher order or more realistic models to predict experimental behavior of actual circuit designs more accurately. These higher order simulations can be used to make further modifications of electronic circuit designs before spending the time and the money to build an actual prototype. In systems that contain more mechanical elements, in addition to or instead of electrical elements, a physical model can supplement a mathematical model or even replace it. A physical model is often a copy of the actual design, but smaller and using cheaper or more readily accessible materials. The purpose of a physical model can be to test out basic concepts in the design and to identify limits over which the design will or will not work. A physical model can have a wide range of very specific goals to support development of the design, or broader goals in simply conveying the scope and basic structure of the design so that the design team can be on the same page when discussing preparations to construct a prototype. Another valuable type of model is the conceptual model, typically used to lay out a 30,000-foot view of a system in which the design fits or takes part. Conceptual models often help designers understand the nature of the inputs to and the outputs from the design, or can help frame underlying hypotheses for how the design should work in a larger system. The conceptual model is often called the big picture and can help communicate the application and the purpose of the design. Yet another valuable type of model is the logical model, which often lays out the signal flow for an engineering design. The logical model puts to paper, or other visual aid, how signals move conditionally through the design and can help expose gaps, missing pieces, or other vulnerabilities in the signal flow throughout the design. Engineers use a wide range of models in preparing to finalize a design. Conceptual, logical, mathematical, and physical models are the major types of models that serve the purpose of preparing to construct a prototype for a design. Regardless of how many different types or in what combination these models are used, they are often sufficient to generate results, insights, and design modifications for construction of a subsequent prototype. Sometimes, however, complex designs use models to support simulation of the design, in whole or in part, prior to the construction of a prototype. This is particularly true of electronic circuits, very small systems at the micro or nano scale, or very large systems at the national or global scale, or otherwise complex designs whose behavior can be hard to predict from models alone, thus meriting extensive simulation. Fortunately, a broad range of software is available to support simulation, from SPICE for circuit simulation to Atlas for device modeling to Automation Studio for control systems design. Wherever a complex design has application in society, a simulation tool usually exists to support further design and advancement. In summary, models are a valuable tool to support simulation or construction of a prototype, and should rarely be skipped during rigorous engineering design. Today, we have looked at the major types of models that can be used to support engineering design. Thank you for joining us. We certainly hope that this session has stimulated you to create a few models of your own engineering design prior to building them, and that you'll join us again as we take a detailed look at other phases of the engineering design cycle.